In physics, symmetry plays a fundamental role. Imagine a perfect square. It looks the same when rotated by 90, 180, 270, or 360 degrees. This is a rotational symmetry. The standard model of particle physics, which describes the fundamental particles and forces, also has crucial symmetries, but sometimes these symmetries break. Let's explore how. There are two main kinds of symmetry breaking. The first is called explicit symmetry breaking. If we change our square into a rectangle, we explicitly break the rotational symmetry. The rectangle only looks the same after a 180-degree rotation. The 90-degree symmetry is gone. In explicit symmetry breaking, the rules of the system themselves change. The equations describing the rectangle would not be invariant under the same rotations that left the square invariant. This is a fundamental difference between explicit and the second type, spontaneous symmetry breaking. Now, let's consider spontaneous symmetry breaking. In this case, the laws of physics stay symmetric, but the ground state of the system, its lowest energy state, does not exhibit the symmetry. A good example is ferromagnetism. Above a certain temperature, called the Curie temperature, the spins of atoms in a material are randomly oriented. There's no preferred direction, exhibiting full rotational symmetry. But below the Curie temperature, these spins spontaneously align in a particular direction, creating a net magnetic field. Another example is crystallization. When a liquid cools and turns into a solid crystal, the continuous translational and rotational symmetries of the liquid are spontaneously broken. The liquid is the same anywhere, then the atoms within it lock into place. The atoms arrange themselves in a periodic lattice, which only has discrete symmetries. Let's now visualize spontaneous symmetry breaking with the Mexican hat potential. It's also sometimes called the wine bottle potential. Imagine a hat where the height represents the potential energy of a field, denoted by the Greek letter phi. This field, phi, is a complex number. At the center of the hat, where the field phi is 0, the potential energy is high. The minimum energy lies not at the center but in a circular trough or valley around the central bump. The shape is perfectly symmetric if you rotate it around.